All right, today's material is kind of a synthesis of the last week or so of material. We're going to do a concept called curve sketching. And I want to list out all of the components of what we mean when we say that we're going to do curve sketching here. Okay? The first thing we're going to do is we're going to analyze the original function. So we're just going to look at what characteristics does f of x tell us? What's the original function tell us? And this is a lot of the stuff that you do in a college algebra course. You just look at the original function and you find things like intercepts. You know, is there any x-intercepts? Is there a y-intercept? You go ahead and find those values so that you can plot them on your graph. Okay? You look for things like asymptotes. Is there any horizontal or vertical asymptotes that might help us sketch out a graph of a function? Okay? So we'll be looking for these types of things. Intercepts and asymptotes will be the major two things that we look for on the original function. So that'll be the first phase of this problem. Okay? The second phase of curve sketching is that we now want to analyze the first derivative. And this is what we spent a lot of the time on the last week. Okay? Analyzing the first derivative tells us things like where the graph is increasing and where it's decreasing. And it tells us the location of any maximum or minimums. Okay? And so we'll be doing a lot of this type of analysis as well. And then the final thing, which is what we just discussed last time, is now we can also go one more step, and that is analyze the second derivative of the function. And the second derivative of the function, what we decided last time, tells us any inflection points that we might have. And it also tells us concave up and concave down. Okay? And so what our job will be is we'll have a function, we'll try to identify all these things within the function, and then try to piece all of this together to come up with what the graph of this particular f of x would look like. Okay? Now, I know the question that's going to come up right away. Okay? Well, we've got a graphing calculator. Why would we want to go through and do all this calculation when I can just plot this thing in my calculator and it spits out most of this information or this answer for me? Well, the reason is because there are certain times in functions some of these things are hidden. Okay? Now, the first couple of examples I do today won't have anything hidden in them. We're just going to try to get through the process with one that we can easily see on the graphing calculator and verify that, yeah, we're doing this correctly. Okay? But as we progress through here, we'll try to get to some examples where we may, the graph we graph it on our calculator, it may just look like it's, maybe barely increasing or constant going across, when in actuality there's a little bit of a hump on the inside there and there is a maximum. Or there's a change in concavity or some other feature. Okay? Because when you get into the applications or you get into the word problems that deal with this, we're interested in finding a lot of times where do we have a maximum profit. And if we just look at the calculator and we don't see where that maximum's at, we may miss out on an answer to a question. Okay? Or there's also many applications for where concavity is positive. That tells us certain things in problems. Okay? So we need to be able to go through this calculus to find out where these different values are located. Okay. The first example we'll go through is just strictly a polynomial, and a nice polynomial, a pretty easy one here. Okay? X to the fourth minus 8x squared plus 9. All right, if I just start by analyzing the original function, we're looking for intercepts and we're looking for asymptotes. Okay, so let's start with this. Okay, any intercepts that we get? Well, intercepts are nice if we can find easy ones or nice ones. We don't really want to have to graph this to look for certain intercepts because that kind of defeats the purpose of this curve sketching. Okay? You can usually always find the y-intercept because it's really easy to sub 0 into a function. And in this case, if I sub in 0, I get what? I get 9. So I have a y-intercept at 0, 9. That's always an easy one to get just in your head. Okay? The question then becomes, are there x-intercepts? Are there values where if I set this function equal to 0, that I can find those solutions? And my guess is that probably there are some x-intercepts. But do we have a nice way or a really quick way of solving x to the fourth equations equal to 0? Not really. I mean, there are some algebra techniques that we could use to find these answers, but if they're not nice solutions, then we don't want to spend too much time on them. Okay? So there probably are some x-intercepts, but we'll just skip them for right now. Okay? All right. Second thing, do we have any asymptotes in this graph? First of all, do we have any vertical asymptotes in this graph? No, okay? What do we need to have a vertical asymptote? Well, we got to have division, don't we? Okay, and since there's no division here, we don't have any vertical asymptotes to worry about. Okay, and in terms of horizontal asymptotes, again, we usually look for division within a problem, so the answer is no. We really don't have any asymptotes to be worried about on this particular graph. Okay, all right. We can also, when we're talking about asymptotes, this is kind of in the same boat here, but we can talk about end behavior of a graph. Okay? Since this is a positive x to the fourth type graph, okay, where's my end behavior? You know, if I just look at the graph, if I look on the left side, is it going to start up here at the top or is it going to start at the bottom? Okay, it starts at the top. And again, this is something you talk about in college algebra. It might have been a while since you thought about this. But positive x to the fourth starts at the top. We don't know what's going to happen in the middle. Where does it end up? Top or bottom? Top, right? Because positive x to the fourth is a lot like positive x squared in the fact that both branches go up to infinity, right? Okay, so we have a little bit of idea about the end behavior of this graph as well. Okay? All right, so that's step one, is just analyze the original function, get as much nice stuff as you can out of it. Okay? All right, now we go to the second step where we analyze the first derivative. We're looking for all of these things that we pick up on from the first derivative. All right, so my first question, well, what is the first derivative of this function? Just a bunch of power rules here, yeah. 4x cubed minus 16x, and the derivative of 9 is 0, right. So just a quick cubic function this time. We set this equal to 0, and we look for factors. Okay, what can I factor out of this? Definitely take out a 4x. What's left? X squared minus the other 4, sure. Okay, and then the question becomes, can I do any factoring or solving with this? You know, what are the solutions out of this? Yeah, okay. If you're comfortable factoring difference of two squares, you'll see that this is x plus 2, x minus 2. If you don't remember that, if you set this equal to 0 and solve it, you'll get 2 and negative 2 as your answer. So either way. So what are my three solutions here? Well, I get 0 from this, I get 2, and I get negative 2. So these are three possible places for maximums and minimums. Okay? How I find out where those are at is I set up intervals. Okay? Go from negative infinity to negative 2, negative 2 to 0, 0 to 2, and 2 to infinity. And I pick a point in each one of these and I test them. Okay? Now, the nice thing is when everything's factored, we can test very quickly because we don't care about the answer, we just care about positive and negative. Okay? So if I pick a number like negative 5, what do we have here? Negative times, careful, negative 5 minus 2. So negative times negative times another negative. So this the whole product is negative. So this is decreasing, right? Okay? And that makes sense because if we look back at our end behavior here, didn't the graph start up here? It's pretty much got to be decreasing to start with. Okay? All right, then we get to a number like negative 1. Okay, this is negative times negative times positive. So this is positive, so we start to increase. Okay, therefore, what has to happen at negative 2? Has to be a minimum, right? It was decreasing and then started to go back up. So x equals negative 2. Well, let me just put it up here. At negative 2, we've got a minimum value. Okay. All right, between 0 and 2, if we keep doing this, just to speed this process up, I know this one's decreasing and I know this one's increasing. Okay, we just pick our intervals just like before. So what's happening at 0 then? 0 is a maximum, and at x equals 2, decreasing changes to increasing, so it's another minimum, right? Okay? Okay. We've done this a lot, so I don't need to spend all the time going through every single one of them. Okay? So we've done all of our analysis of the first derivative now. We've got all the maximum minimums, we've got all the decreasing and increasing places. The only other thing that might be helpful for us is if we get some y coordinates for each of these places where we have a maximum or a minimum. Now I've already got the y coordinate for 0 because we said earlier that was 0, 9. Okay, so when I come over here to my actual graph when I'm finished, I can plot these points and I can see exactly where those maximum minimums are at. Okay, and we'll do that when we get to that stage. Okay, step 3 then is now we want to analyze the second derivative. Pick out all the concave up and concave down and inflection points. So the first question, what is the second derivative here? (12x squared minus 16). And again, I set this equal to 0. That's where I get possible inflection points. And you can do this one of two ways. You can either try to factor something out, or we can just solve it algebraically. Probably just be just as easy to solve it. Okay? If I add 16 to both sides, and then I divide by 12, okay, and then square root that result, I'm going to get two different x values. Oh, whatever the square root of 16 over 12 is, plus and minus, it's not going to be a nice number, but whatever those values are for x, those are my possible locations for inflection points. Okay? How do I check for sure? Well, I set up intervals. I go from negative infinity. What is this as a decimal? I heard some of you typing it in. How much? 1.15, okay. So from negative infinity to negative 1.15, we'll check for concave up or down. Then we'll go from negative 1.15 to positive 1.15, and then I'll go from 1.15 on to infinity. And I want to find out, well, what should be true about the concave up and concave down here? Okay. Well, what if I pick a number like negative 2? If I sub it into the second derivative, okay, what's negative 2 squared? Be 4 times 12, 48. 48 minus 16 is definitely positive, so what's happening in here? Concave up, right. Okay, if it's positive, it's concave up. Okay. Now, I'm going to jump down to this one here, because if I pick negative 2 up here, what if I pick positive 2 down here? Aren't I going to get the same answer? Because negative 2 squared and positive 2 squared are the same thing. So this one will also be concave up. And if I choose 0 in this one, what type of answer do I get? Negative, so this is concave down. So do I have inflection points? Do I get a change from concave up to concave down or vice versa? Yes. Okay. So I have both of these values here are inflection points. Okay. So I have a rather large group of information here that I can now piece together to try to draw the graph of this original x to the 4th function. Okay. So let's kind of come over here to the side. And let's see if we can finish this off. What should a graph of this function look like? Okay. Well, we decided that 0, 9 was one of our ordered pairs to begin with. Some other nice ordered pairs would be if we could locate where these are at, where these minimums are. Okay. So what if I sub in 2 into this function here? This will be 16, 25 minus 32, so negative 7 if I did that right. Okay, so it looks like we've got a value at 2, negative 7. And if I sub in negative 2, I'll get the same thing. I'll get negative 7 again. Okay, and so we should now be able to give a pretty good sketch using our end behaviors from before. We can get a pretty good sketch of what this graph looks like. Okay, definitely it appears to come down, hit at this minimum point, negative 2, negative 7. Then it will go back up. It will hit this maximum at 0, 9. Okay. Then it decreases again, and then it increases again, goes back up to infinity. Okay. Now, where is the inflection points, or where are the inflection points at on this graph? Okay, we've located where they're at numerically. Okay. If I had to guess, and this is why we go ahead and use calculus to solve this, since I have a minimum at negative 2, and a maximum at 0, I would have guessed that this graph is concave up all the way until it gets to 1. You know, if I'd had to guess, I'd have picked right in the middle of those two numbers is where it would stop being concave up and start being concave down. But apparently it's not quite right at 1. It's just a little bit off to the side. Okay? So we can go ahead and find the inflection points. That'll tell us where we have kind of an inverted parabola, and then over here it's back to concave up again. Okay? Like I said, this is a really simple example. We could have picked a lot of this stuff out just by graphing it on our calculator. We can find these points really easy. We can see a pretty good graph right away. Okay? But this is just an illustration of what it means to do a curve sketching example. I mean, there's a lot of work involved in this here. Okay? All right. Let's pick another example that isn't quite as nice as this one here. And let's see if we can do the same thing. Let's see, let's take x squared divided by ln of x. Okay. Now, within the curve sketching idea, step 1 is to analyze the original function. Now, I didn't list this over here, okay, but probably one more thing I should have included in here is to also look at any domains that you might have. Now with the polynomial one we just did, there wasn't any problems. We can do anything with x. Okay? This example has some major domain issues. Okay? First of all, we've got division. And so is there any number that I could plug in here for x that would turn this denominator into 0? The natural log of what is 0? And the natural log of 1 is 0. So definitely right away, for a domain, I see x definitely cannot equal 1, or I will be dividing by 0. Okay, so that'll be one problem on my graph. The other problem is, just because we have a natural log function in here, what numbers can you take the natural log of? Can I take the natural log of -2? No. So I have a problem with negative numbers. Can I take the natural log of 0? No. Again, that's a problem. So the only types of numbers I can even sub in here for x are anything bigger than 0, as long as it's not 1. So we have some domain issues right away with this graph. So we don't want to be looking for any graph on the left side or on the negative side, because there won't be anything there. Okay? All right. What about any intercepts? Okay. Do I get a y-intercept on this? No, and the reason is, can I even sub in 0? No, we said we can't do the natural log of 0. So there will not be a y-intercept. Okay? Can I set this thing equal to 0 very easily? Okay? And find any solutions? Well, yeah, fractions are pretty easy to set equal to 0 because we kind of ignore the denominator and we look at the numerator. What number can I square and come up with 0? 0. But again, can I have 0 as an x-coordinate? No. Okay, so we go ahead and we test it and we try to find any intercepts, but we're not finding any this time. Okay, everything is all at 0, 0, and we don't have the availability of x equals 0. Okay, so no intercepts on this graph. Okay, what about any asymptotes or end behavior type stuff? Okay, well, we've got a definite problem at x equals 1, don't we? Okay, and if I sub in 1, I get 1 divided by 0. That's an asymptote. Whenever you get something else divided by 0, it's an asymptote. So definitely x equals 1 will be a vertical asymptote on this graph. Okay. As far as end behavior on this graph, this one's not going to be quite as nice as the polynomial here, but let's look at it. Okay. What if x gets really, really large? As x goes off to infinity, what might happen on this graph? Okay. Well, this number gets really large, doesn't it? A large number squared is even bigger. Okay. The natural log of infinity, the natural log also increases. So as I put in bigger numbers, this also gets bigger. So we've got a little bit of a power struggle here. This one's trying to get bigger, this one's trying to get bigger. So we really can't tell at this stage what's going to happen. Okay? So for right now, we don't know. As x goes off to infinity, we can't tell. Okay? What about as x goes off towards 0? Now, I'm not going to negative infinity here, and the reason is because I only get, my domain says just go to 0 and then stop. Okay, so I'm just going to say, well, as x gets close to 0, what happens? Okay, so what if I put in a really small number like 0.001? What's 0.001 squared? In other words, it's 0.001 times itself. Well, it's even smaller, isn't it? It's getting closer to 0. So the numerator's getting closer to 0. What's the natural log of 0.001? Well, if you try it, it's going to be a really big negative number, or a really small negative number, however you want to look at it. Okay? But what happens if I take 0 divided by anything? That's 0. So I really don't care what this number is, because this is getting really close to 0 here. So it looks like the y value is also getting really close to 0. And that makes sense with what we talked about before. This is saying that we're getting really close to the origin, and isn't that kind of what we were hinting at up here above? We're kind of thinking we might get close to the origin. Okay? Now we won't get there. There'll just be an open circle at the origin, but this is good evidence that, yeah, that's really what's happening here. Okay? All right, so there's all of our first, just original function analysis. Okay? All right, now we go after derivative number 1. Okay, which rule do I need to use here? Okay, Jeffley quotient rule. Okay, and the quotient rule says you take the bottom piece times the derivative of the top. Derivative of the top would be 2x minus the top piece times the derivative of the bottom. What's the derivative of ln of x? 1 over x, yeah. You hadn't had that one for a little while. And then all divided by the bottom piece squared. Okay? Now, just looking at this initially, it doesn't look very promising. It doesn't look like, wow, this is going to be kind of messy to solve equal to 0, but it actually works out fairly nice. Okay? First of all, this cleans up to just a what? This is just x, right? So I've got ln of x times 2x and then minus just x. Okay, so that helps because now what can I factor out of this numerator? I can factor out an x. I've got one of them here and I've got one of them here. Okay, so I factor out the x. I've got 2 ln of x left over from the first part and a minus 1 left over from the second part. Okay, now I keep writing the denominator, but it really doesn't matter, right? Because if we're going to set this equal to 0, we don't care what's going on down here. Okay? What's my solution from this first factor? 0, but can I have 0 as a solution? No, okay, because it's a domain problem. So it worked out mathematically, but we realized from the original problem we can't have it. Okay, so no solution from here. Do I get a solution from this other piece? Well, let's try it. 0 equals 2 ln of x minus 1. Do a little bit of algebra. Add 1, divide by 2. And now the hard part is, how do we solve this for x? You've got to remember your rules for logarithms here. Okay? Natural log is the same as logarithm base e of x. And the question is, how do I rewrite this in exponential form? Okay, and I know it's been a while since you've done this, but this will be e to the 1/2 equals x, right? Okay? It's just by definition. That's how you switch from logarithm to exponential form. Okay? It's this base to this answer equals this number here. Okay? And so I have a possible maximum or minimum at whatever e to the 1/2 is. Okay? Or the square root of e. Okay? All right. Then I set up my intervals. Okay? I don't need to go all the way to negative infinity. I only need to go back to 0. So my first interval goes from 0 to that square root of e. And the second interval, let's see, I should back up 1 second here. This is one of my critical numbers. I have another critical number. Where else is a critical number here? Where else did we have a problem at the beginning here? Okay, at the vertical asymptote of 1, right? Okay, and I just about forgot to mention that. Okay, so here's one of our critical numbers. The other critical number is at x equals 1 for that asymptote. Okay, so now I've got a little bit of a question. I need to know which one of them is smaller. Is that number smaller or is 1 smaller? 1 is smaller? Okay, so my first interval then just needs to go from 0 to 1. The second interval will go from 1 to that square root of e, and the third one goes from the square root of e on to infinity. Okay? All right. I look at picking a number between 0 and 1. I plug it into the first derivative, and this will be the easier form, and I need to find out positive or negative. Definitely the denominator is what? Because it's squared, definitely positive. So I don't have to worry about it because I'm dividing by positive. Okay? If I pick 0.5, okay, 0.5 is positive. The ln of 0.5, negative. Negative times 2 is still negative. Minus 1 is still negative. So negative times positive 0.5 is negative. So what's happening in here? Decreasing. Okay? And you may need to plug some stuff into your calculator, especially with this one. These aren't nice numbers here. Okay? Then I would plug in value between 1 and whatever this number is. I don't know what this decimal is. 1.65. So maybe I could pick 1.5 for this interval. I would plug it in here, and what do you come up with for a result? Is it increasing or decreasing? And we don't really have to do the denominator because that's still positive. My problem is I just don't know how big ln of 1.5 is. Ln of 1.5 is, okay, so this is 0.4 times 2, so 0.8. 0.8 minus 1 is negative. Okay, and that's what I needed to know. Negative times positive is negative, so this is still decreasing. Okay? Now, this one I can be a little safer on. If I pick a really big number like 100, the ln of 100 is definitely positive. Times 2 will make it even bigger. Minus 1 will still be positive. Okay, so positive times 100 is still positive, so this is increasing. Okay? So what do we have at e to the 1/2? Yes, minimum, because it's decreasing and then it starts to go back up. Okay, so this is a minimum value. Okay, good. All right, so there's first derivative analysis. Okay, second derivative analysis, trying to pick out concave up and concave down. All right, this is going to be a little tougher here. Go ahead and erase this as well. All right, we want to work with the nicest form that we can come up with on this first derivative, and I would guess it probably would be this. I really don't want to do any multiplication in the numerator. I'd rather leave it separate, because if I do that, then I've got to do a quotient rule, and then I've got to do a product rule at the same time. And that'll make it a little bit of an issue. Okay, so let's take the derivative of this. Okay, so quotient rule says I take the bottom piece. This might get messier than what I want here, but we'll go ahead and try it. Times the derivative of the top. Well, I still got to do a product rule, don't I? Okay, what's the derivative of this right here? Okay, well, I write the ln of x. I write the first part. What's the derivative of the second part? Whoops, right here. Derivative of that is 2. Okay, so I'll put the 2 out in front. Okay, plus the second part times what's the derivative of ln of x? Yes, okay, 1 over x. All right, so there's my product rule, and then minus derivative of x is 1. Okay, so bottom times the derivative of the top. Whoops, that's a minus. Okay, minus the top, ln of x times 2x minus x, times the derivative of the bottom. Derivative of the bottom. Okay, what do I do with this 2? Out front, so 2 ln of x to the first. Okay, and then I look inside the parentheses, and what's the derivative inside? 1 over x. So I said this is probably getting messier than what I really want, but we'll go ahead and keep going here. And then divided by the denominator squared, which would be the ln of x to the 4th. Okay. All right. Yeah, this got to be a pretty good mess here. We'll see if we can come up with any solutions out of this. Okay. First thing that I notice is that I can cancel off one of these ln of x's. So I don't have to worry about any multiplication with it. Okay, second thing, all of this is just what? This is just a 2, isn't it? X divided by x cancels. Okay, so that's all just a 2. And I think that's pretty good. All right, now let's go ahead and start multiplying this through here. Okay, so I've got 2 ln of x squared, because I've got one of them here and one of them here. This is just a 2 ln of x. And this is just a minus 1 ln of x. So I can actually take 2 minus 1 and get 1 ln of x out of that. Okay. Okay, then over here, all right, if I do distributive property, it looks like I've got 2 times 2, which is 4. This x and this 1 over x cancel. And so the only thing I have left is 4 ln of x. Do the rest of the distributive property right here. This 2 is still there. This x and this 1 over x cancel off. Okay? So it actually simplified quite a bit. Okay? Just all the way down to a 2, yeah. Okay. Again, if I'm setting this equal to 0, I wouldn't have to worry about denominator. And so the question would be, can we get anything out of this numerator? 2 ln of x squared minus 3 ln of x minus 2. Okay? Can we get anything out of this as a solution? Well, what does this kind of looks like? Does it kind of look like a quadratic equation? 2 times something squared minus 3 times something minus 2. So it kind of looks like a quadratic equation. And so we might be able to actually do some factoring, just like we do with other quadratic equations. You know, I put a 2 ln of x on the front and an ln of x here. Okay, I need to come up with a couple of numbers that multiply to give me 2. So 2 and 1. Let's do it like this. And I need to get the outside and inside to subtract to be negative 3. Looks like it works. Okay. If I do it this way, okay, because now my outside is negative 4 plus 1, which would be negative 3. Okay, so this thing actually factored out even for us. Now we try to go through and set each one of these equal to 0. Okay, and try to solve these and see what values of x we come up with here. Okay, this one, we're running out of time here pretty quick, so I'm going to fly through them here. Subtract 1, divide by 2, and then we have e to the negative 1/2 if we switch it over to exponential form. Okay, so this is a possible place for a inflection point. And then this example would be e squared, giving us another possibility for an inflection point. Okay. Now, at this stage, I would set up my intervals, setting it up 0 to this number. Okay. Then from this number to 1, because 1 is still a critical number from before, 1 to this number, and this number to infinity, and I can test each one of these for concave up and concave down, and then determine if there's any inflection points involved in this graph. Okay. Like I said, this one got messier than what I had hoped for. No way that this would ever be a test question, okay, because it just got too much. Okay, but we can do pretty good analysis even with messier functions to begin with. Okay.